Chapter 10, Human Alteration of the Atmosphere. 10.6, Human-Caused Climate Change. So a word that's been used quite a bit in the media is global warming. Scientists are reporting that climate data is showing that temperatures over land and ocean has been increasing. And this pattern of increase has been occurring for quite some time. I'm going to show you two maps. One showing the change in annual mean surface temperature for a period 1901 to 1960. And it indicates that over much of the world we've been seeing an increase in temperature. There are some cool spots here, but for the most part the pattern that is seen is one of warming, where white indicates no change in temperature, so the temperature has stayed pretty much constant between this period 1901 to 1960. Blue, slight decreases in temperature, and yellow, orange, and red increases in temperature, with red being most significant. So that's a 60-year period. Let's now look at the roughly 60-year period between 1961 and 2017, and we see that the blue almost completely disappears. There's still a few areas where there hasn't been any climate change. So that's for this period, 1961 to 2017. But over most of the globe, and especially over the continents and at high latitudes in the northern hemisphere, there have been significant increases in surface temperature in these areas. This change is global warming. But humans aren't just causing changes in temperature. There's also changes occurring in terms of temperature, the storminess of the planet, and more importantly, change in extreme weather. The following three graphs come from the Intergovernmental Panel on Climate Change science volume in the last IPCC report. And what we see here is climate change as modeled in pink with our enhancement of the greenhouse effect. The black line represents actual observations. And then another model run done with just natural forcings, no greenhouse effect. So for land surface, we see that there is a big disconnect now between observations and the temperature that should occur if you modeled with just natural forcings. The modeling with the greenhouse gas enhancement, greenhouse effect enhancement, does correlate with the observations. The middle graph shows combined land-ocean surface, and then the final graph just looks at ocean heat content, how it's changed, observations, model predictions with anthropogenic forcings, and model changes with just natural forcings. So there, once again, we see this disconnect. So here is a list of the 10 hottest years recorded globally, and it's relative to a baseline of the temperature of the planet between 1881 and 1981. And we can see that the warmest years have all occurred roughly in the last decade. And the temperature scale on the side shows how warm these years were, and these are global averages relative to that baseline. So in 2016, we were some 1.25 degrees Celsius warmer than that baseline. Last year, about 1.2 2021 was the temperature recorded. Here we see these lines represent mean monthly temperatures for a whole bunch of years, actually years going back to 1880. So each line represents a year. They're not all labeled, but what is labeled are the hottest years on record. And we can see the last 5 are 2020, 2016, 2019, 2017, 2015. The white line represents that baseline period for 1881 to 1910, and we can see how different the temperatures are now relative to that baseline that is over a century old. This graph shows individual years back to 1880, and the green line represents a trend line, a 7-year moving average trend line. We've got data all the way up to 2019, and we can see that it looks like global warming began in about 1905. There was a gradual temperature increase to about 1943, 42, then a decline and a leveling off, and then global warming began again starting in 1970 and continuing on today. And the rise now is much steeper than it has been during any part of this period. That hiatus period between mid-1940s and mid-1970s, we know what caused that. It was related to changes in the dynamics between the Pacific Ocean and the atmosphere in terms of it exchanges heat. And it was also due to our loading the atmosphere with reflective particles that dampened global warming for about 30 years. And then those particles reached an equilibrium. They're not increasing in any significant way anymore. And in fact, they're decreasing, and the warming took off again. So how have human activities caused global warming, this form of climate change? And there's other things that are occurring too, as I said, changes in precipitation, storminess of the planet. Much of this has been caused by our activities causing an increase in the concentration of particular greenhouse gases, the main one being carbon dioxide, but also methane and nitrous oxide. And this was done via burning fossil fuels, the conversion of natural habitats into agricultural fields, and deforestation, the removal of trees, and allowing cropland or other forms of less biomass intense vegetation to exist. By the year 2050, scientists predict that carbon dioxide content in the atmosphere will be about 550 parts per million. So an increase of about 100% from pre-industrialization. It's currently tracking at about 415, 416 parts per million. So to predict the future, climate researchers use complex computer models called general circulation models, or GCMs for short, to use mathematics and physics and our knowledge about how the climate system works to predict the future state of the climate. We also run these models backwards to predict or to prove what has occurred was due to the modification of things like the greenhouse effect. When these GCMs are modeled with higher greenhouse gas concentrations in the atmosphere, they always predict a much warmer climate. So these global circulation models consist of a whole bunch of boxes covering an imaginary Earth. Each one of those boxes carries out a series of calculations. The boxes exist in the horizontal and the vertical. They're all connected because, of course, circulation in the Earth's climate is is connected. It moves about the planet, so you have to have the boxes connected. Some of the things that are simulated in this model include clouds, precipitation, Earth's radiation, solar radiation, heat and moisture movement between the atmosphere and the ocean, sea ice coverage, and the albedo of the Earth's surface. The Intergovernmental Panel on Climate Change, or IPCC, publishes the results of different GECM simulations. They've released 5 different reports. The 6th one's about to come out, and they forecast how the climate is going to change due to a range of possible outcomes or scenarios. In fact, they have 4 main scenarios. One called RCP 2.6, so that's a low rate of emission of the greenhouse gases, carbon dioxide, methane, and nitrous oxide. RCP 4.5, which is the next highest, RCP 6.0, and RCP 8.5. And RCP 8.5 is the worst case scenario in terms of emissions of greenhouse gases into the atmosphere into the future. The GCM output concludes that the Earth's future global warming will be somewhere between 1.1 and 4.8 degrees Celsius by the end of the 21st century. So that's additional global warming to what already occurred. So here we can see graphs displaying emissions of carbon dioxide, methane, and nitrous oxide under the different scenarios. And the numbers represent how many watts of energy is being added to the Earth's climate system. 2.6 at the lowest scenario, and 8.5. It's pretty much too late for us to keep emissions to RCP 2.6. The best case that we can predict for the future is with conversion to renewable energy, that we level off at RCP 4.5. So this graph describes the global average surface change under these 4 different emission scenarios. And we can see that for the worst case scenario, RCP 4.5, we're talking about an increase in the amount of heat energy in the global system, an increase in global mean surface temperature of about 4 degrees. And there's a range because they use many different models. Each model is tuned differently, and that range is anywhere from roughly about 5.5 to about 3 degrees with a mean of about 4. Also shown on this is the best case scenario. But for the best case scenario to occur, this RPC 2.6, we would have to start reducing emissions of greenhouse gases immediately and reaching sort of no net emission of carbon dioxide, methane, nitrous oxide by about 2050. So what can we expect with future climate change? We can probably expect winters to be warmer in the mid-latitudes, anywhere from 3 to 5 degrees Celsius. In the Arctic, it's going to be a much greater increase in temperature, anywhere from 10 to 15 degrees Celsius. And this is also occurring in high elevations. So the higher the elevation, the more warming that's occurring. A warmer planet would increase evaporation of water, and this should lead to higher quantities of precipitation. Precipitation should increase in the future in along the equator and in the middle to high latitudes. Hurricane intensity and frequency would increase. We're already seeing more intense hurricanes, not necessarily more frequent. So here, these graphs from the IPCC 5th assessment report shows predicted future changes in surface temperatures under RCP 2.6 and RCP 8.5. So they're comparing. The comparison is between a baseline period of 1986 to 2005 to the last 10 years in the 21st century. So we can see for RCP 8.5, the temperature rises are going to be highest with latitude, higher latitude, and highest over the continents. Precipitation changes are shown below in graph B. So under RCP 8.5, we can see wetter tropics, drier subtropics, and wetter mid-latitudes and high latitudes. We should see more extremes of temperature and precipitation. Southeast Asia and Central Africa may experience stronger monsoons because of climate change. And we should also see changes in the frequency, the number. There will be more thunderstorms, and the strength of them will increase. Here's a nice graphic from a website called Climate Central, and it looks at how will climate change certain characteristics of locations. We're looking at New York City, and the characteristic we're looking at, the climate characteristic, is days above 35 degrees Celsius temperature. So on the far left, we see the current situation. We have roughly 2, 3, 4 days normally per year where the temperature goes above 35 degrees Celsius in New York City. By 2050, we're looking at, under both emission scenarios, current and moderate, in the low 20s to mid 20s. Let's skip all the way to 2100. By 2100, under the current emissions, high emission trend, New York City will probably experience over 50 days where temperature rises above 35 degrees Celsius. Under a moderate emission scenario, so roughly RCP 4.5 to 6.0, we could limit that to only 40. Future climate change is going to change the geographic extent of Earth's major biomes. Plants and animals are going to be influenced in terms of where they can live. They have particular adaptations to ranges in temperature and amounts of precipitation. Many animals and plants will be forced to migrate, and if they can't migrate, they will die out. Scientists are predicting that many species are going to go extinct because of climate change. So these animals and plants need to change their geographic location. We've seen coral reef diebacks because of increasing sea temperatures. In the future, we're going to see more of our plants' coral reefs be destroyed by rising ocean temperatures, where the temperatures are just going to be too warm for the organisms that construct coral to survive. In terms of the hydrology of the planet, sea level has been rising for over a century. Much of this rise is due to thermal expansion. Melting of glaciers and ice caps and sea ice will add a lot more. If we look at the glaciers on our planet, 95% of them are in rapid retreat right now. The hydrology of the planet is going to change in some areas. Water levels in many lakes will change. Some will increase, some will decrease, depending upon temperatures and rates of evaporation. There will be changes in water supply and storage. Currently in BC, a lot of water is stored in mountains where it accumulates as snow and then is released in the spring to fill up lakes and rivers. Well, that's going to change. The amount of snow that is going to fall on the mountains is going to reduce. There's going to be less snowpack. We're going to have a completely different hydrology in the future in terms of much of BC, where water is supplied by melting snow and ice in alpine areas. This animation shows the change in Arctic sea ice in terms of It's ground coverage in square kilometers, millions of kilometers. So there's a graph and also a satellite imagery of the extent of this coverage, and you can see the decrease that's occurring. It starts accelerating in about the year 2000, and the data goes to 2015, and there's an obvious trend of decreasing Arctic sea ice. So this is the sea ice coverage during the summer months. Future global climate change is going to affect human health. There's going to be more mortality due to extreme heat. A recent study has indicated that there's going to be a significant increase in days that are too hot and too humid for people to survive in parts of India and Southeast Asia. There's going to be an increased risk of tropical and subtropical infectious diseases as they move with warmer climates. In our built environment, urban areas will get warmer, and this will increase the need for air conditioning. There will be construction problems with homes, roads, and pipelines in the high latitudes as permafrost melts. There will be changes in agriculture. We're going to have to change where we can grow particular crops. And my own research deals with how is climate change going to influence ski resorts. And ski resorts are going to be influenced by warmer temperatures and changes in snowfall, increases in rainfall. So here we see winter mean temperature modeled for a number of ski resorts along a longitudinal gradient that go from Vancouver Island to the border of BC and Alberta. So Castle Mountain is in Alberta. Sunshine is half in Alberta, half in BC, Fernie's in BC. And the black dots represent historical average winter temperatures for a 30-year period between 1901 to 1930. The red square with an X, white X in it, represents the average temperature in 1981 to 2010. So a 30-year period that just occurred just 10 years ago. And you can see the rise, how temperatures have changed. The green represents future temperature by the year 2071, 2100, and that's under the best case scenario, the RCP 4.5. The blue diamond represents the worst case scenario, RCP 8.5. So with this temperature change, we're going to see a shrinking of the ski season. It looks like for based on our data right now, the sort of threshold when skiing can't occur is about -1 degree Celsius. So Cyprus right now is having problems. Now the interior resorts are different. They're cold resorts. They have a much longer season, but they get less precipitation. The reason why the interior resorts can function at warmer temperatures is because of the amount of snowfall they get. And of course, snowfall will occur at any temperature below 0 degrees Celsius. This graphic comes from the work of my MSc student, Masters of Science, Ethan Clark. He's going to defend his thesis at the end of November. And here we see some of the major ski resorts that exist in Western Canada. And in this, he models how is the length of the ski season going to change under the worst case scenario, RCP 8.5 for the year 2085. So you can see the coastal resorts are all looking like they're going to have a 91 to 100% reduction in ski season. Big White, somewhere between 46 and 60%. The most protected resorts are the ones furthest away from the coast. The ones in the Rocky Mountains, they're looking at about a 31 to 45% decrease in ski season. Here's a single graph of the change in ski season for Whistler Ski Resort from Ethan's research work. So the red line models when the ski season begins. For Whistler Resort, we're using a temperature of -2 as the timing of when the ski season begins. This is the temperature at which you can make artificial snow. So on average, between 2081 and 2010, that date was somewhere in the middle of November. The end of the ski season took place about mid-March. So that graph, the red line beneath the blue line, which is the temperature -2 degrees, defines the ski season. The green line measures what's going to happen for the year 2085 under the worst case scenario. What will the average monthly temperatures be? And you can see that they're well above that -2 degree threshold. So are we doing anything to reduce the impact of human-caused climate change? Scientists and politicians have been busy. In 1992, an actual framework convention took place dealing with the problem of climate change. And about 5 years later, a protocol or an agreement was signed that involved the first sort of attempt at limiting greenhouse gas emissions. The agreement suggested that they should try to reduce greenhouse emissions by 5% relative to what occurred in 1990. Now, many of the nations didn't achieve this, or they bailed out, including Canada and the United States. Just a few years ago, there was another agreement called the Conference of the Parties, Paris Agreement. So it was based on the Kyoto Protocol, but asking for more serious mitigation efforts. 177 parties agreed to further reduce the greenhouse gas emissions, except for the United States. And it was agreed that what they're going to try to do is limit global warming to 2 degrees Celsius, relative to pre-industrial. We've already had about a 1 degree increase. So, and if possible, try to limit climate change to only 1.5 degrees Celsius relative to pre-industrial values. And as I said, 2016 is about 1 degree Celsius above pre-industrial. So a lot of work ahead. Computer models predict we will pass the 1.5 degrees Celsius threshold under the current emissions trajectory around 2045 to 2050. To limit warming to 1.5 degrees Celsius, greenhouse gas emissions must begin decreasing immediately. And we need to get to zero emissions of greenhouse gases, and that includes carbon dioxide, methane, and nitrous oxide by between 2040 and 2050.